Hello there. So this is the second part of the first prac on NAND gates, which you would have completed on breadboard, the other circuit that you can see here. You would have completed these ones here, and now we're going to be doing the simulation on Circuit Wizard. So I'm going to walk you through those steps using the Circuit Wizard Student Edition. So I've got mine open up right now. Just maximize it, and first thing I need to do is get some NAND gates to create that circuit. So under the gallery, the right hand side here, and then we're going to go to Logic Gates. I'm just going to select the NAND 2-input NAND gate that I can see there. Click on it once, and then I can place it on my display. Using my mouse wheel, I can zoom in and out, and I'm going to Control C to copy, Control V to paste, and I'm going to get my 3 gates that are needed there. So looking at the connections here, you can see that the 2 inputs of these 2 gates are connected together. So just clicking on the pins, you can see that I can connect them together, and also the outputs of the first 2 gates were connected to the inputs of this 3rd gate here. And now I'm going to be able to add an input here and here, and if I double click on it, I can give it a label. Let's call that one A, and this one B, and similarly for my output, I can put an output on there, and I'm going to call this Q, and there's our circuit. And in order to get it to simulate, the play button or the run button up here on the toolbar, we've got logic low, which if I hover over it, you can see that it's saying 0 volts there. That's logic low, and if I click the button there, if I hold there, it says 5 volts. That's a logic high. Let's stop the simulator for a second. I'm actually going to select the Logic Levels tab on the left here, and this, when I run the simulator, you can see it actually tells me what the logic level is at different points of the circuit. So I don't have to hover over it and try and figure out whether it's logic low or high. I can see. Okay, so now what we're going to do is, for this gate configuration, we're going to complete this truth table, and you can see here that C corresponds with the output of the first gate, and with 0, 0, that C is there, and that is a logic 1. Similarly, D, which is the output of this second gate here, is also going to be logic 1. So if I go back to there, I can put a 1 in both of these columns here. And if I go back to the simulator, I can see the output is logic low. So coming back here, we had 1, 1, that was 0. Okay. I'm going to have to, in order to make the simulator work, I need to be able to switch between the things, so I'm going to erase the line each time, unfortunately. So you can just record that as I do each line. Okay. So now I'm going to change it to a 0 and a 1. So A 0 and B 1. And you can see here that C is still a 1 and D is a 0 and Q is a 1. So I'm going to have C is a 1 still, D is now a 0, and our output was a 1. Okay. And similarly for our 1, 0 input, so 1, 0, we've got C 0 and D 1, and Q is 1. So that was 0, 1, Likewise, if I now make them both ones, both inputs are high, these are both 0, and the output is 1. So they're both 0, 0, and 1. Okay, so we had the outputs should look something like this, and this is typical for an OR gate. So an OR gate is if A or B or both of them are logic high, logic 1, then the output is logic 1, otherwise the output is logic low. And this is the Boolean symbol for an OR gate, and in fact if I go back and replace this lot, so I need to stop the simulation, I'm going to replace this lot with a 2-input OR gate, and we run the simulation again. So 0, 0, so 0. If either of them is high, it's a 1. The output is 1. Like so. So the OR gate is actually in practice made using 3 2-input NAND gates internally inside the chip. Now the NOR gate we can create by simply inverting the output of an OR gate. So if I undo what I did there, and now what I can do is just cut and paste another 2-input NAND gate, connect the inputs together again to make it an inverter, connect it to the output, and put the output Q on the output of that 4th gate there. And now basically what we should see here is that C and D should be exactly the same as what it was before. E will be the Q as we had before, because E would be this point in here. And now Q is going to be the inverted of that. Okay, so what we should have for this is this should be a 0, a 1, a 1, and a 1. Okay, and we can expect that since Q is just going to be the inverted E here, that we should see a 1 there, and the rest being zeros. Okay, so the NOR gate we can create using 4-input, 4 2-input NAND gates like this, and it should behave exactly the same as the inverted output of the OR gate that the NOR gate that we made. So if I were to run that simulation, we've got 0, 0, and here is our E column, which is a 0, just like we had for the OR gate, and now we invert it, and that gives us a 1. If I change both both of these inputs to high, that E column goes to high, and the Q here goes to low. You can see that that's for all those possible conditions there. So you can see here that the output would be just like what we said it was. It would be 1, 0, 0, 0. Now the Boolean expression for the NOR gate is, so if we've got 2 inputs A and B, so it's A or B, so or we use the plus, but now we're inverting not just either one of these, we're inverting the whole lot, so we put a bar right across the whole lot there, and that's equal to our output Q. Okay, so OR gate is A plus B is A or B. And here's NOR, A NOR B, looks like that. Okay, so the XOR gate is a little bit more complicated. You can see here we've got sort of 3 layers of gates here, and not all of the connections are dependent on the previous layer. So this middle layer of gates here, some of them are connected directly to the input, some of them are dependent on this gate output here. So let's create this in Circuit Wizard. So I can leave my inputs there. And I'm just going to clean up bits that I don't want. Okay, so we had one NAND gate there like so. We had 2 NAND gates like this, and they were both connected to. So one input of each of these NAND gates is connected to the output of this first gate, and the other inputs are connected like so, and then we've got another NAND gate on the output there. Place that there. Okay, so here we have the configuration like we've got set up here. Now we've got that circuit there set up, and what we should see is if the inputs are the same, the output is low. If the inputs are different, so if this is a 1, it's different than this one which is a 0, then the output is high. Likewise, if we've got a 0, 1, the output is high, but if they're both 1, the output is low. So in this circuit here, we've got labelled C here and D here, and Q is the output. So C is this point here, and so when they're both inputs are 0, both of these are 1, and the output is low. So it would be C and D both be 1, and Q would be 0. So they'd be 1s, that'd be a 0. Okay. Now if I look at with A, oops, let's just use this one. So if A 0 and B 1, we've got a 1 for C and a 0 for D, and Q is a 1. So we've got 1, 0, 1. 1, 0, 1. Similarly, we've got A is 1 and B is 0. So C is a 0, D is a 1, and Q is a 1. So that'd be a 0, 1, and that's a 1. Okay. Now if I go back to having them both high, you can see these are both 1s now again, and D is a 0. Q is a 0. So we got 1, 1, it's a 0 there. Okay. So the total truth table output should look something like this. Now remembering the Boolean expression for XOR is a bit like the OR, so it's a plus, but we put a circle around it. Sorry, that's okay, so that's XOR symbol there. So it's a plus with a circle around it. And this is the gate symbol for an XOR. And just like before, we could replace all this with an XOR gate. Which in reality would probably be made using 4 NAND gates inside. And you can see here that both inputs are high, the output is a low. If the inputs are different, the output is a high. If the inputs are both low, the output is low again. Okay. So this behaves identically to that circuit that we just created. And similarly, I'll leave it up to you as an exercise. You could use, you could make an XNOR gate by simply inverting the output. But if you were to do this, you're going to need a fifth gate. And well, let's show you what would happen if I do a fifth gate. Notice how all these are labelled IC1, A, B, C and D. So let's add a fifth gate here. Let's just move the output along. I'm going to copy this one and paste it. Notice that now it says IC2A. And that's because the NAND gate IC, so the 4011, has 4 NAND gates internally. So 1, 2, 3, 4. In order to get a fifth one, I would need a second IC if I was to build it using discrete components.